Okay, welcome everyone to this week's online causal inference seminar. Today we have Thijs van Ommen from Utrecht University giving a talk to us about graphical representations for algebraic constraints of linear structural equation models. His co-author, Matthias Sturton from Technical University of Munich, is joining us today for the Q&A. So please submit your questions and Matthias will help Thijs answer the questions throughout the seminar. Our discussant today is Rohit Bhattacharya from Williams College, and the Q&A will be handled by Emma. You want to say a few words, Emma?
Yeah, thank you. So hi, everyone. We are taking questions today through the Q&A as always. So there's a button at the bottom of your screen called Q&A. Please submit your questions through them. You can submit them anonymously or not. This Q&A helps us track the questions and helps us make them public to everyone once the speaker answers them. So Matthias and Thijs are both taking questions, so please submit as many as you'd like. And yeah, I'll let you now start, Thijs, whenever you're ready.
Okay, thanks. I'll share my screen. Right, so indeed, this work, as mentioned, is joint work with Matthias Sturton. It was published last year at BGM, Conference for Probabilistic Graphical Models. So if you want to see the more technical version of the story, you can find the paper there. Right, so what is this about? Yeah, so we're talking about linear structural equation models here. So a linear structural equation model takes a form like this. So for each variable, we have a structural equation which is linear in, well, the other variables. There can be an intercept term, and there can be noise. Typically, we assume it's Gaussian noise. And importantly, we do not assume that these noise terms are independent. So these models are used often in various areas by practitioners, and also to model causality. Not always, but they can be used to model causality. So that's the reason I'm speaking to you about it. So for such a model, we can draw a graph like the following. So in this graph, the directed edges represent that there is, for instance, variable A appears in the equation of variable B. And also the bidirected edges represent that the corresponding noise terms may have non-zero covariance. So those are the ones that may be correlated. The ones that do not have a bidirected edge between them are required to be uncorrelated. So it is through these bidirected edges that linear structural equation models can also talk about latent confounders. So the latent confounders are not represented explicitly, but these bidirected edges account for the possibility that they may exist. And further, also, it's possible to have both a directed and a bidirected edge between the same between two variables. So that's called a bow, and even directed cycles are allowed in general. So that makes these models very general, and this is a very rich class of graphs. Well, that's what we want to talk about. Though, in practice, I will not be saying very much about the case of directed cycles today. Okay, so now what we want to do is we want to describe the model that is defined by such a linear structural equation model, and here we mean model in the statistical sense. So it is the set of all the distributions of the variables in the linear structural equation model, all the distributions that could be obtained by choosing different values for the parameters, the lambdas and the omegas. well, identical to omegas, but the lambdas over here and the omegas for the non-zero covariances over here. Okay, so such a model then describes exactly what distributions could arise, and in the case of a linear structural equation model, each distribution can be specified by its covariance matrix. So essentially, we'll be talking about sets of covariance matrices. And so what we're trying to do here is to describe the set of covariance matrices that could arise from a given graph of this form. Now, it is well known that for DAGs, so directed acyclic graphs, the model can be described by listing the conditional independence constraints. And then there's many tools like d-separation, for instance, that allows us to link graphs and probability distributions, and a huge amount of useful results come from this. For instance, many causal discovery algorithms for DAGs. So that's also the goal we have in mind for linear structural equation models. Right, so I mentioned causal discovery. So this is, in the most idealized case, it means that the only thing we get is a bunch of data, and then we put it into an algorithm, and out comes the correct graph that generated these data. Now, this is possibly too idealistic in many practical cases, but still knowing the model can be useful for other reasons. For instance, we would still want to know, given two graphs, if it is even possible to distinguish them based on observational data. Or sometimes it only becomes possible to distinguish them if we make additional assumptions. So knowing the model will help us to answer all sorts of questions like these. However, so in the case of DAGs, we have the conditional independence constraints that describe the model. In the case of linear structural equation models, those do not suffice anymore. And here's an example. This will be a running example in a large part of this talk of a linear structural equation model that does impose a constraint. So the model is not the set of all possible covariance matrices on 4 variables, but it is limited in a strong sense. But the way in which this model is limited cannot be expressed in terms of conditional independencies. Also, it cannot be expressed in terms of some other already well-studied generalizations of conditional independencies. So, for instance, there's nested Markov constraints, as they have been called by Spitzer, Evans, Richardson, and Robbins. That's one generalization of conditional independence, which is mostly which is perfectly suited for the case of non-parametric and discrete variables. But it turns out that in the case of linear structural equation models, other constraints can arise. And specifically for the linear case, there have been vanishing tetrads and generalization by Sullivan, Talaska, and Dreisma. So vanishing tetrads also have a very long history, and more recently, this has been generalized, and the theory looks nicer now. So there's now also a graphical criterion for these, namely T-separation, which is very similar to D-separation, for testing this type of constraint. So this is specific to the linear case. However, this constraint is not of either type. So there is yet further generalization needed in order to describe the models of linear structural equation models. Okay, so what we'll do is, let me first say that from algebraic geometry, we'll be needing a few terms occasionally. So first, the word algebraic, which here means that algebraic constraint means a polynomial equality. So we have some polynomial in entries of the matrix sigma, of the covariance matrix. And this polynomial is required to be 0. Then it's a polynomial equality. And this is, in fact, the polynomial equality that is needed to describe this graph over here, the model of this graph. In addition, in general, also semi-algebraic constraints are needed. So those are also polynomials, but not equalities, but inequalities. But for the set of graphs that we'll be talking about today, actually inequalities do not play a role. And even for graphs in which they do play a role, I would argue that it's more important to know about the algebraic constraints than about the semi-algebraic constraints. For many purposes, these are stronger restriction of on the model than these ones. So for that reason, I would focus on the algebraic constraints. Right. So even in the type of graph that for which the model does impose inequality constraints, I would focus on the algebraic model, which is sort of a closure of the actual model, where we add all the additional sigmas. We still leave out the sigmas that do not satisfy the algebraic constraints, but we ignore the semi-algebraic constraints. So anything that fills the semi-algebraic constraints gets added to this thing with respect to this. Okay, so that explains the word algebraic in the title. Now, the motivation for this research is that these polynomials have drawbacks. They are hard to work with because sometimes they can get very large. So this is both difficult to even to write them down would take a lot of paper, though computers would still be able to deal with that part of the problem. But if you want to understand what is going on in this polynomial, you cannot really look at it and understand it. And also the algorithms that exist in algebraic geometry. There do exist algorithms that to which you can pass the equations of a linear structural equation model, and they will compute the polynomial constraints, the algebraic constraints. But these algorithms can sometimes be very slow. So sometimes they'll run in a couple of seconds, but other times, even for small graphs with 4 or 5 variables, they can take days or weeks to finish the computation, and you do not know ahead of time which case you will be in. So this makes them very impractical to work with. So what we are doing here is we are presenting a different way of writing down these algebraic constraints, namely in a graphical form. So here's an example of a graphical constraint. And this is in fact the graphical constraint, again, corresponding to this algebraic constraint. And so this algebraic constraint gives a more succinct representation than straight up writing the polynomial. Right, so the graphical constraint is an undirected bipartite graph, and each of its nodes is labeled by, in general, a set of the variables from the linear structural equation model. So I'm claiming that these graphical constraints can largely take the role of the polynomial constraints. So for that to be true, we need to have a way of converting a graphical constraint into a corresponding polynomial constraint. And that's then as follows. Basically, we write down the adjacency matrix. Because this graph is bipartite and I've drawn it in a zigzag fashion so that this is one part and that's the other part, then we can take one of the parts to be rows and the other part to be columns of a matrix. So here C corresponds to the first row, A to the second, B to the third. And similarly, the columns are over here. And now we fill in this adjacency matrix by putting sigmas, so entries from the covariance matrix, into the corresponding matrix over here, depending on the labels that were on the nodes of the graphical constraint. And well, the adjacency matrix needs to reflect the structure of the graph. So in particular, there is no, this C is not adjacent to this A, which means that the first row and the third column, where this C and that A intersect, there will be a 0 instead of this sigma. So in this way, for each graphical constraint, we construct this matrix. And then finally, for this matrix, we take the determinant, and that determinant is then the polynomial that we wanted to represent. So this is how these graphical constraints correspond to polynomial constraints. Okay, before we go on, let me give some examples of how these graphical constraints also represent the more well-known cases of algebraic constraints, because algebraic constraints are a generalization of conditional independence and nested Markov and of the vanishing tetrad and generalizations. So each of those are also polynomials, and well, almost all of those, it would appear, can be represented as graphical constraints. So definitely, if we have a marginal, let me say that right. If the constraint that this covariance, this observed covariance, is 0, that would be represented very simply by this graph. So this graph would then generate a 1-by-1 matrix, and saying that the determinant of this matrix equals 0 is exactly saying that sigma AB equals 0. And now, as I mentioned in the linear structural equation models, we're usually assuming that the noise terms are Gaussian. And that's because in the Gaussian case, having this covariance equal to 0 is equivalent to having independence. Right, so that's the marginal independence. Similarly, for conditional independence, in the Gaussian case, that corresponds to having a vanishing partial correlation. So this is the notation for partial correlation. So those correspond to a conditional independence between A and B given C. And that would take this form. So it would again be a graphical constraint of 2 nodes. So the graph over here has 2 nodes, and each of those, one has the label A, the other has the label B for these A and B. And both of the nodes are labeled with the conditioning set. So in this case, the conditioning set has 1 element. If there's more elements in the conditioning set, they would all appear both here and here. So this way, also graphical constraints can represent vanishing partial correlations, which correspond in our case to conditional independencies. Then very similarly, the vanishing tetrad constraint would take this form. So it's quite similar to this, except that here there's no, the intersection between this and this is empty. Right, and indeed the vanishing tetrad constraint is known to be defined by the determinant of a particular matrix being 0, and that's exactly the matrix that we're constructing here. Okay, so those are some known cases, but these graphical constraints can all can represent much more general polynomials. So one of the bigger ones I could find among 5 variable graphs is this one. So here we have a degree 9 polynomial that's being represented by this graphical constraint over here, which is not in one of those previously well-studied categories. So right, I'm also not yet in the position that I can say very much about this polynomial from looking at this graph, but I'm hoping that this will be a good first step to know that that the polynomial can be represented in this way, and hopefully that will help answer some questions at some point. Okay, maybe now is a good time to see if there's any questions in the audience.
Hi, Thijs. So we don't have open questions now. We do have a comment from Ilya. Should I read it out, or we can? So Ilya wrote, I should say the fact that the constraints in the nested model are all equality constraints implied by a DAG factorization on the observed margin is due to a paper by Robin Evans called Margins of Discrete Bayesian Networks in the AOS, which he thought could be added to a slide, but yeah, just a comment.
Okay, right. Yeah, I cited only one of those papers here. There's many papers by those authors that consider, in particular, nested Markov constraints and maybe also quite closely related things.
There is actually, Matthias pointed out that it would be good if Thijs explained the point or an example on slide 4 in detail. There was a question about that, apparently, that Matthias answered. The no conditional independence point is what.
Okay,
yeah.
Right, yeah, so here we have, so in this graph, I'm claiming that there is a constraint, but it's not a conditional independence constraint. So indeed, I can explain that a bit better. In this graph, we have 5 edges, which corresponds to having 5 degrees of freedom. Well, at most 5 degrees of freedom in the model. It could be that the model has fewer degrees of freedom if it turns out that those degrees of freedom in the parameters aren't free. However, there are 6 degrees of freedom in the off-diagonal elements of sigma. So this is why I claim that there is a constraint here. The model is 1 dimension lower than the set of all possible covariance matrices. Right, and this constraint is not conditional independence. Well, you can try that by checking d-separation. No matter what you condition on, C and D will always remain D-connected, which means that there's no D separation and thus no conditional independence to explain the constraint. And also for any other pair of variables, clearly they are D-connected because, well, they're adjacent. And a different way to see this is, by the way, via the, what's it called? Well, there's another way to see this other than by checking the D-separations. Right, so there is a constraint, but it's not a conditional independence. And similarly, you could check for this and this that it's not of those forms either.
Great, thank you, Thijs. Please continue.
Okay. Right, so next I want to say something about, before I go into the next part, I'll give a bit of background about the identifiability problem. So this is a different problem than what we're talking about here, trying to find the constraints to describe a model. The identifiability problem is given a graph to see if it's possible to recover the parameters from sigma. Right, so this is a question that's very important also to practitioners. Maybe they have a linear structural equation model in mind, which they believe generates their data, or which they want to use to model their data at least. And they want to use this to determine the size of some causal effect. And for this, they would need to be able to compute the parameters of the linear structural equation model from their data. If the model is not identifiable, then this might not be possible. So then they would need to do something different. And it's good to know this before they gather their data. However, the identifiability is a bit of a strong requirement. So a weaker requirement is generic identifiability, which is the same except that it allows some small subset of the parameter space to exist, which maps to some sigma, and other points in the parameter space map to the same sigma. So then for such parameters, we would get a covariance matrix out for which we could not uniquely recover the parameters because there could have been multiple parameters behind this thing. So a prominent example where this occurs is in this so-called instrumental variable model. So this is used if we want to determine the causal effect of B on C. right, and yeah, this is not identifiable, but it is generically identifiable, and the difference occurs when the parameter on this arrow is 0. If this arrow is has parameter 0, then you can see that any covariance matrix you get out has only sigma BC not equal to 0, and then there's infinitely many ways to distribute, to attribute that to either this directed edge or that bidirected edge. Okay, so generic identifiability is more relevant, I think, in practice when dealing with linear structural equation models than identifiability. For identifiability, a graphical criterion exists that says exactly whether the graph is identifiable or not. But for generic identifiability, this is more difficult. And the biggest advance in this area is the half-track criterion. There's actually both a sufficient and a different necessary condition presented there. I'll only be needing the sufficient condition here. So if a graph satisfies this sufficient condition, then we know it's generically identifiable. So a graph that satisfies this condition will be called a half-track identifiable graph, or HTC identifiable graph. Now, I won't be needing the details of this criterion in this talk, but one thing I will need is the half-track itself. So a half-track is either a directed path or it's, well, almost a directed path, namely the first edge is bidirected, and after that, all edges are directed towards the destination. So those will come up soon. Okay, so I presented these graphical representations, but then some questions are, how could we find those graphical constraints given the graph of a linear structural equation model? Well, let's start with that question. So what I'll be describing now is an algorithm into which we can put any, well, not completely any linear structural equation models, but only the half-track criterion identifiable ones. Well, the half-track criterion has some certificate, which I'm calling curly Y. Yeah, and this certificate basically, together with the graph, allows you to verify that indeed the graph is half-track identifiable. And then this algorithm will output a list of graphical constraints that hold in the linear structural equation model. So
before we move on, sorry, Thijs, I think there was a question in the audience about how these graphical constraints are transcribed to polynomials.
Okay.
Could you explain that operation again?
Oh, sure. Yes. So a graphical constraint in general looks like this: a bipartite graph. So because the graph is bipartite, some of the elements can be, some of its nodes can be made called rows and the other columns, so that every edge connects a row to a column. And then we construct this matrix like this, where, well, for each row, there will be a row in the matrix here. And for instance, here we have the row C, so that's the first row, and it's adjacent to this column. Well, there will be a column for B and a distinct column for D. So those are the first two columns here. And then because there's an edge between the two, there will be non-zero elements here. And specifically, they will always be sigmas, so entries from the covariance matrix, capital sigma, indexed by these two labels, so the C and the B, or in this case, the C and the D. And now the C isn't adjacent to this column, so that's why there's a 0 here. So this is how we construct the matrix. And then after that, we take the determinant of this matrix. So this times this times this, minus this times this times this, etc. And out comes a huge polynomial. Well, not so huge in this case, but in general, they can be pretty large. And this polynomial is then the algebraic constraint.
Maybe a simple follow-up question. How do we know which nodes are rows and which nodes are columns in this graph?
You can choose it either way. It will just mean that your adjacency matrix gets transposed. and then it would have the same determinant, so the same polynomial would come out. There's one thing that I was sweeping under the rug now, namely if you choose the order of the rows or the columns differently in this matrix, then you could end up flipping the sign of the polynomial. So yeah, to be exact, we are only specifying the polynomial up to sign, but we're okay with that because we're only interested in these polynomials because we want to know whether they're zero or not.
Okay, thank you.
Great. Okay, so I think we're now at the algorithm. Right, so the algorithm works for any half-track identifiable graph, but here I'm presenting a slightly simplified version for the case of both free acyclic path diagrams. So those are the special case of our graphs where we do not have both. So no bidirected and directed edge between the same between two variables, and also no directed cycles. So for this class of graphs, the algorithm will work as follows. We'll look at all the pairs of variables that aren't adjacent. And for each of those, we'll start to form a graphical constraint by this very simple two-node constraint of the two adjacent variables, non-adjacent variables. And after that, for each of those graphical constraints we're constructing, we will expand both nodes, which basically means that we're growing them into trees. So this expansion operation means that we add some more labels into this node, and also we add some new nodes that sprout off a node like this. And finally, this operation may be performed recursively. So let me clarify that by an example. So here's again the graph we've been seeing before. So in this graph, there's only one pair of non-adjacent variables, C and D. So we'll only start one graphical constraint, namely this one. But it's not done yet. First, we need to expand both the C and the D over here. So let's start by expanding C. Then we look in the linear structural equation model and see that C has no parents. So this means that we have nothing to add to the node's labels, and also we have no new nodes to create. So expanding this node is a zero operation, and we're already done. So we only need to expand the node D over here. The node D does have a parent over here, namely B. So to expand the node D, we add B to its label, and we create a new node with B as its only label. Then the next step is to check if we need to recursively also expand B. And for this, we check if there is a half track from the child over here back to the parent. So that would be a half track from D to B. And indeed, in this case, there is such a half track, namely this thing is a half track from D to B. So because this half track exists, we need to recursively also expand B. So we do that, and same as before, we see that it has one parent over here. So we add A over here and a new node with an A over there. And now we go to A and we see that this time there is no half track from B to A. So we do not need to recursively expand A, which means that now we have expanded everything we needed to, and we're done. Right, so this shows how the algorithm works for the case of both free acyclic path diagrams. In the general case, it's slightly different because it also depends on the half-track criterions certificate. But yeah, this is enough to give you an idea of how the algorithm works. Okay, so now we have these graphical constraints and we have an algorithm for constructing them. Now the question is still, in what sense exactly can we say that these constraints describe the model? And the thing that we can always say is this implication. If a covariance matrix belongs to the model, that implies that all graphical constraints are 0. So if we take the entries of the sigma, we input them into all the polynomials that come out of these graphical constraints, then all of them will evaluate to 0. And by the way, because we do not need to represent these as very big polynomials, but just as determinants, this computation can be done very quickly because a determinant can be evaluated quite quickly, while a very long polynomial could take more time just by its size to evaluate. Right, so that's one implication, but the implication in the other direction, unfortunately, doesn't hold in general. There can be sigmas that are not in the model, but that nonetheless satisfy the constraints. So that's a limitation of these descriptions at this stage. But fortunately, there are, this case arises only in specific circumstances. So first, there's again these small holes, these small sets, specific covariance matrices that are not in the model, which are not pointed out by the graphical constraints. They're not pointed out by the polynomial constraints either. So we haven't lost anything by going from polynomials to graphical constraints. And well, these are rare anyway, so it's not too big of a problem. But there's two more serious cases where larger regions of this form can arise, larger regions outside the model that are not excluded by the constraints. And they are of two types. Either they are sigmas for which the Hofstra criterions computation of the parameters, if that works by solving a sequence of linear systems, and if it encounters a singular matrix at some point, then we're in a case where we cannot guarantee the reverse implication. Another case happens only for graphs with directed cycles, because if there's a directed cycle, then it can happen that we compute the Hofstra computation outputs parameters for some sigma which was outside the model, but this sigma, but these parameters do not actually compute back to the sigma. So that's specific to graphs with cycles. Okay, so here I want to add some more terminology from algebraic geometry, namely ideals, and specifically also prime ideals. So what we're basically doing here is the algorithm generates a set of graphical constraints. Each of those represents a polynomial, and these polynomials are supposed to be describing the model. So this is the situations studied in algebraic geometry, and there these sets of polynomial constraints would be called an ideal. And the nicest kind of ideal that we could hope to get here would be a prime ideal. And indeed, a prime ideal exists for any algebraic model that we could get from any linear structural equation model. So indeed, the prime ideal is the perfect case for us. We would hope that our algorithm always outputs a set of graphical constraints that translate to a prime ideal. So I won't define them exactly, but one aspect is that a non-prime ideal may describe a set of points which are the union of several of the sets described by several prime ideals. So each of those subsets would then be called a primary component. So sort of a prime ideal always has just one primary component, but non-prime ideals can be decomposed sometimes into multiple primary components. And to help intuition a little, let's look at the case where there's only one polynomial in the ideal. Then this ideal is prime exactly if this polynomial is irreducible, so if it cannot be factored into multiple non-constant factors. Clearly, if there are two non-constant factors, then the original polynomial is 0 if and only if one of those equals 0. So either one is then defining a component of the ideal. So this is how you can see that a non-prime ideal might describe a set that decomposes into multiple components. Right, so the prime ideal is really the perfect case from an algebraic geometry point of view, but for our purposes, we can be a little easier. Namely, we can decide to focus our attention on just positive definite matrices, because a covariance matrix is always positive definite. We only need to be interested in those. So we call an ideal PD primary, so positive definite primary, if it has the following property that a sigma is in the algebraic model, if and only if all the constraints are 0 at this sigma. So here we do have an if and only if, but we just needed to restrict our attention to positive definite sigma. So in the again, for intuition, let's look at the one polynomial case, the case of an ideal that contains only one polynomial. Then suppose that this is the polynomial that comes out of our algorithm. If this polynomial can be factored in such a way, so there's an actual prime polynomial, one that's irreducible, and but it's multiplied by some sigma AA. Then the set of sigmas for which this constraint is 0 equals the right set that satisfy the actual prime constraint. But there's also a spurious component in the primary, a spurious primary component where sigma AA equals 0. But if sigma AA equals 0, then the sigmas that have this, they're not covariance matrices. They're not positive definite. So we are quite happy also in this case, even though it's not a prime ideal. And now a proposition is that if the graph is ancestral, then the algorithm will always output a PD primary ideal. So in particular, this means that for a DAG or a MAG, a maximal ancestral graph, always the algorithm will output a PD primary ideal, but also in the more general case of non-maximal ancestral graphs. Okay, then let me very quickly go to the next case. There's a third case of what I call I primary ideals, where they do not have the nice property of PD primary ideals, but they do have, but we can still tell apart which of the components are spurious and which is the real component, because the spurious components exclude the identity matrix, and no linear structural equation model would ever exclude the identity matrix. So we can tell that those components cannot be the right one. And so in some sense, this ideal does give us all the information we need to describe the model. And for these also we have a proposition. So if we have a Beaufry acyclic path diagram, then always the algorithm will output an I primary ideal. Okay, so in the previous slides, I used for intuition the case that the ideal contains only one polynomial. But if there's more polynomials, then things get more complicated. Then it's no longer possible to factor those polynomials, and from those factorizations decide what kind of ideal we're dealing with. But this may also be determined by certain interactions between the different constraints. So let's give an example where this and also some other problematic features appear. So in this linear structural equation model, there's 8 edges. Well, I only explained the algorithm for the Beaufry case, and this graph does have both. But it's still going to be the case that the number of constraints produced by the algorithms will equal 5 choose 2, so the number of pairs of variables minus the number of edges in this graph. So it will always produce 2 constraints. However, the prime ideal that describes the algebraic model behind this, it requires 3 constraints to be described, namely these 3 vanishing tetrad constraints. And now if you try to describe it with just 2 constraints, for instance, if you try to leave out this constraint from an ideal, and yeah, you hope that your ideal still describes this model, then your ideal will give rise to a spurious primary component. In the case of leaving this one out, it would be a spurious primary component defined by these equations. So this is not a D primary or an I primary ideal, but this is an ideal that actually describes some linear structural equation model, but not the one we're trying to describe. So this is very misleading as a description of the model. So in the general case, beyond I primary ideals, we need to watch out for this possibility. So that's the bad news. Now, I wanted to get an idea of how expressive these graphical constraints are. So are we losing much compared to writing down actual polynomials? So I tried a bunch of things in order to answer that question. Yeah, basically I did a computational study, and I'll show you the results in the next slide, where for each algebraic equivalence class among 5-node acyclic linear structural equation models, I tried to find, well, specifically linear structural equation models that impose exactly one algebraic constraint, because those are easier to analyze computationally. For each of those, I try to determine if there is a graphical constraint that describes this model. Well, the main tool is to run the algorithm and see what graphical constraint comes out. Sometimes it's worthwhile to try it with different half-track criterion certificates, because then it will the algorithm will output a different constraint. Another thing I did is to run it on different algebraic equivalent linear structural equation models within each equivalent class, because again, then we get different constraints. If those don't help, then we can also use the idea that because we are representing these polynomials as determinants, we know that applying basic row and column operations on an adjacency matrix will not change the polynomial, will not change their determinant. And many such operations do still correspond to a graphical constraint. So still a matrix with either a 0 or a sigma of the right kind in each cell. And if all else fails, I also tried brute force search for a bunch of the smaller remaining cases. So then the result is that among all those equivalence classes, there were a bunch, 17 out of roughly 400, for which there was no half-track identifiable graph among the equivalence class. And then I couldn't run the algorithm, and also most of those were too large to apply brute force methods or anything else. So for those, I don't have an answer. But for the remaining ones, even though these are very general graphs, so they are allowed to contain both, so they don't satisfy the conditions for either of the propositions I listed. Still, it turns out that there was always a PD primary graphical constraint that existed, able to describe this model. In fact, in the majority of those cases, a prime graphical constraint existed. So what I'm saying here is that even though the propositions seem to say that only in specific cases can we guarantee that we get a PD primary or an I primary constraint, in practice it turns out that very often the nicer kinds of ideals actually do exist and can be written as graphical constraints. But also there were two other equivalence classes where it turned out that the algorithm could only produce a constraint that's PD primary but not prime. And according to the brute force search, indeed there exists no graphical constraint corresponding to the actual prime polynomial. So this graphical constraint represents a polynomial which is equal to this spurious factor times the actual prime polynomial. And there is no graphical constraint that describes the prime polynomial exactly. So it seems that it might be out of reach to always get a prime constraint. And it's possible that for larger graphs also things get even worse. But in this case, at least, it was still possible to get this PD primary constraint, and that's basically good enough for any purpose we might have in mind. Okay, then let me wrap up with the conclusion that it seems from this computational study that many of the algebraic constraints, almost all, I would even say at this point in a very vague way, these algebraic constraints can be expressed sufficiently well as graphical constraints. So these graphical constraints do seem to be a useful tool for taking a large part of the role of the polynomial constraints. But there's also a lot of future work involved, and I'm only listing a few of those of the steps here. So first, we saw that computational results look way better than the theoretical results. So can we improve the theoretical results to also give guarantees that reflect the status that we see in the computational results? Then another question is, right now the algorithm only works for half-track criterion identifiable graphs, but there have been a number of extensions of the half-track criterion since the original. And so it would be very interesting if an algorithm could be devised that can also leverage these generalizations of the half-track criterion in order to find different constraints. Right, and as we saw, the algorithm often produces spurious factors. So I listed all the ways in which I try to get rid of those spurious factors in the computational study. So it would be great if we could do that in a more automated way. And finally, well, not finally, but the final thing on this slide is that it would be great if there could be a graphical separation criterion along the lines of d-separation based on these graphical constraints. So thank you for your attention. And then I think Rohit will want to say something.
Thank you, Thijs, for the great talk. I think we're a bit short on time. Let's skip all the live questions and let Rohit give his discussion first. Thijs, if you could unshare your screen, we can let Rohit share his.
All right, thank you. I'll try to keep this short so that we can head to some questions. Okay, so thanks for a great talk. I'll preface this by just saying that a lot of my intuition comes from non-parametric identification and thinking about non-parametric equality constraints, but I'll try my best to give what I think are interesting open questions in these linear structural equation models and hopefully inform some interesting future research directions. So I have a simple question, but I don't know if it has a simple answer. And this is something that's been coming up a lot for me as I've started to venture into models that aren't fully identified. So not just due to unmeasured confounding, but also missing data. So the big question I have is, what is the appropriate supermodel to test and observe data constraint? And here's what I mean by that. So in the case of DAGs, it's really simple. Let's say I just have this DAG A to B to C. It suggests that A is independent of C given B. And then if you want to test this constraint, usually what you think of is you maybe think of the graph without this edge as being the null hypothesis and the graph with this edge as being the alternative hypothesis. Maybe you run a likelihood ratio test, and that gives you, you compute some p-value and you choose to reject the null or not. So in DAGs, this is really easy, finding these supermodels to test the constraints that you see. from the DAG factorization are you just say, okay, I'm going to add a directed edge from past to future, and that's generally the supermodel that that you're looking for, and that works very well. So, just as a quick simulation, here's your null, here's your alternative. You compute the parameters using you get the MLE estimates for all these parameters, and then, like I mentioned, you use standard statistical techniques to test that whether this coefficient is 0, essentially. And then you don't actually have to compute all these parameters in the DAG, in the case of DAGs, because the DAG likelihoods are easily decomposable. So you can, in fact, just look at C given its past. You don't actually even have to care about B given A. But because we're going to deal with ADMGs or acyclic directed mixed graphs, the likelihood for those are less decomposable. So in general, let's just think about computing all of the parameters. So here's an interesting case. So this is actually the graph that Thijs was talking about for a large part of the talk, where the absence of the edge between C and D doesn't correspond to an ordinary conditional independence, doesn't correspond to any any of the known constraints like a Verma constraint or even a tetrad constraint. And then the question is, well, here, this is my null hypothesis. What is a suitable alternative? You could think about, well, adding the C to D edge, or you could think about adding C bidirected D edge, or you could think about doing something completely different. You could just move to a DAG supermodel where all vertices are pairwise connected. That would also be a valid supermodel that doesn't have this constraint. It's just non-parametric, or it's just the saturated model imposes no constraints, right? So these each have their advantages and disadvantages. So, so if you think about adding the C to D edge, this supermodel turns out to be almost everywhere identified. So it turns out it's a bow-free graph. There are no bows in this graph, and we know bow-free graphs are almost everywhere identified. It's not actually globally identified. So this turns out to be a non-arid ADMG, and there are different ways to describe a globally identified acyclic linear SEM. But one way is to check whether what are known as confounded trees. Turns out there is a confounded tree here. So this is not a globally identified model. So maybe it's not the best supermodel you could think of. If we think of adding the bidirected edge instead, it turns out this supermodel is globally identified. So maybe a better candidate. And then finally, you could move to a DAG supermodel. So you just convert all of these edges to be directed, have a C to D. So that's also obviously globally identified, but it's in a larger graph. If you change too many edges or add, modify the graph too much, you might accidentally change other constraints in the model. And so you're no longer actually testing the constraint that you want to test. You may be testing for more stuff just by accident, right? So if I just go ahead and compute the MLE estimates, so there was a question raised in chat about how do you compute estimates for these parameters. So one way is to apply what's known as the RICF algorithm. And it's really designed for globally identified models, but it can be applied to generically identified ones as well. And in particular here, I'm using a Python implementation of this algorithm. So you could use either of those two models as your alternative hypothesis, the one where you add the directed edge or the bidirected edge. But if you use the one on the left, standard statistical tests may not have the correct behavior, so you may get a conservative test, for example. And in this case, this would be a rare event because these are generically identified. So in a lot of cases, you will find that this parameter roughly converges to 0, indicating that there indeed is a constraint. But maybe you don't want to risk it, and why not just go for the global smooth identified supermodel, right? So so maybe you're not sold on this being a huge issue because it's rare. But here's a case in which I think it's less rare. So this turns out to be an HTC identifiable graph, and there's a missing edge between A and C. And there turns out to be a constraint between A and C. It's just an ordinary conditional independence constraint in this case, actually. And then you can ask the same question: do I add an A to C edge, or do I add an A bidirected C edge? And you could think about trying to convert this into some DAG supermodel, but I think that would be again, you don't want to accidentally introduce other constraints, right? So it turns out in this case, if you add the A to C edge, this supermodel is still HTC identified. So that's a good sign. However, if you add the A bidirected C edge, the supermodel is no longer HTC identifiable. And I suspect actually that it's not identified at all. And I'm not an expert at applying the HTC criterion and its generalizations, but my suspicion is that it's just not identified in general. And so that's really problematic now. So here your choice is much more consequential. Of if you use the directed edge, run the RICF algorithm, you get nice parameter estimates converging to 0, indicating that there is a constraint between A and C. However, in this case, you just see these crazy numbers, and the algorithm kind of just blows up because you're running it on a non-identified model. So there's a clear choice of what supermodel you should prefer here, I think, but it does raise a question of, is there a general rule, and how do we overcome these holes in our search space? And this kind of goes to what Thijs was talking about, is that, sometimes you encounter holes. So if you think about applying this as a subroutine in a causal discovery algorithm, when you start to think about deleting edges or adding edges, you need to be really careful that when you add an edge, you're not moving to some non-identified model, but then because you have these holes in your search space, you have to worry about, well, are you exploring all possible models in some reasonable manner? So just some forward-looking thoughts, taking these like really nice ideas about finding algebraic constraints, and then trying to move it towards introducing them into causal discovery algorithms. Here's kind of what we know about causal discovery for various classes of ADMGs. So ancestral graphs have been studied a ton. Here's just 3 citations about algorithms for causal discovery and ancestral graphs. And these are a subset of all globally identified ADMGs. And you can think about expanding your search space. You can think about doing search in arid ADMGs. This turns out to be all globally identified ADMGs. And there's, as far as I know, there's just one causal discovery procedure that's been proposed for this class so far. The one that is actually more well studied is Bow-free ADMGs, which turns out to be it's all the globally identified ADMGs plus a few more generically identified ADMGs, right? So it's a subset of all generically identified ADMGs, and here's some references for folks that have been looking into that. And then I'm curious, how do we get to doing causal discovery for, I guess, what I'll call half-track identified or half-track ADMGs, which is a bigger subset of generically identified ADMGs than just Bow-free ADMGs. And I think in a 2018 paper, Thijs and Joris Moy, they did a kind of a semi-exhaustive search on HTC identifiable ADMGs of 5 nodes, and they had some clever tricks for how to move between identified models or identified members of an equivalence class rather than trying to run the MLE estimation on non-identified members. So I'm really excited, and if folks have thoughts and I'd love to chat with you about how do we design more algorithms that touch this space, because I think ancestral graphs have sort of been explored pretty extensively, but there's a lot of room to grow here. And that's all I have for the discussion. Thank you so much for having me.
Thank you, Rohit. We are quite over time, but I'd like still to give Thijs maybe a minute to respond to Rohit's comments, and we can always go afterwards, after we conclude the formal part.
Right, yeah, thanks for the discussion. Very interesting questions that you raised. Yeah, indeed, what I know about dealing with this comes from the work that you refer to. Actually, that was only for 4 variable, not 5 variable case. So yeah, I'm not confident that the brute force-ish approach we use there would also fly for 5 variables. And indeed, the thing I learned there is that it's very important to know, to be able to tell if 2 graphs are equivalent. In our case, algebraic equivalence was the relevant equivalence relation, because then within the equivalence class, you can indeed pick a specific graph that has nice properties. But as long as you remain in the equivalence class, you will get the right answer. So yeah, I think it highlights the importance of knowing the equivalence relations.
Okay, thank you. So let me just try to end the formal part first. I know folks have questions and we can discuss it afterwards. So thanks again to Thijs and Rohit for the great talk and discussion. Next week, we will have Yuhao Wang from Tsinghua University speaking in the seminar, and I think the discussant will be Rajesh Mukherjee from Harvard. So I hope I'll see you next week. How do I stop? Okay, here.